Okay, hey guys, welcome to another wonderful episode of Let's Do Some Maths. Let's do some maths. Today we're going to be looking at still further maths, FP2. We're going to actually be doing two questions today, or two parts of two questions. So, I put about the same amount of effort in, not that you need to know that. What are we doing? We're going to Jan13. So FP2, AQA, Jan13. We're going to be starting off looking at question 5, part C. A nice little 5-marker integration there. And more integration, actually, on the next question. Question 6, part B. So that's what we're doing today. Get the question paper up, open in front of you. Turn it to 5C, that's page 10. It's a follow-on question from part B, but don't worry, I will write that bit on the board, so you'll be caught up no matter where you are. Okay, what 5C wants you to do is to show that question. It wants you to show that the integral between 1/2 and 0 of 4 multiplied by the inverse of the tangent function is expressible as ln of 3 to the power m over 2 to the power n. I bet it says where m and n are integers. Yep, don't even need to look. So when m and n are integers, are part of the z with the weird line down it, that just means the integers. So when m and n are integers, and the bit that it tells you beforehand in the question before in 5b, remember this is going to be following on because it doesn't actually say hence in the question, but it's kind of obvious, that the derivative of the inverse tangent function is 1 over 1 minus x squared. So if you'd been doing this question properly, you would have figured that out in part B. Cool. Okay, so, and it also tells you to use integration by parts. Now the integration by parts formula, I'll write it out in case you forgot it, is that the integral between b and a of u multiplied by dv dx is equal to uv between b and a minus the integral of v du dx between b and a. So what this means is when you've got an integral that's one thing multiplied by the other, you pick one of them to be u and the other one to be dv by dx. Now the u gets differentiated to become du by dx, and the dv by dx gets integrated to become v. So essentially what you're doing is you're choosing one of these to integrate and you're choosing one of these to differentiate. Usually you think which one's the easiest to integrate, or actually you think which one's the most difficult to integrate and differentiate, and you do the opposite of that. Here though, because in part B we're told what the derivative of the inverse tangent function is, that's a very large clue that we're going to be differentiating the inverse tangent function. So I'm going to pick this one to be u and differentiate it to make du by dx, and I'm going to pick this one to be dv by dx, and that's going to be integrated to make v. Now what I do, once I choose those values, I go off to the side of my page and I write them in a little table, a little 2x2 table. So let's do that today. U is equal to tang minus 1 of x. So du by dx from part B is equal to 1 over 1 minus x squared. dv by dx is 4. And if you can't integrate that, you don't deserve to be watching the video. The integral of 4 is 4x. Cool. Now what we're going to do is chuck those, we've got them in the table now, we're going to chuck those into the formula here, remembering that we have got limits. We've got the limits a half and 0. So the integral equals it's on the screen. The integral equals uv, so 4x times the inverse tang of x between a half and 0, minus the integral between a half and 0 of v du dx dx, v du dx dx, so 4x over 1 minus x squared. And this integral here should be firing off something in your brain. You should be seeing that and thinking, oh, that looks interesting. And the reason is because there's one less power of x on the top than on the bottom. On the bottom you've got x squared, one less than that is just plain old x. And what that is suggesting is it might be one of those integrals where the derivative of the bottom is on the top. And the derivative of the bottom being on the top means it's a ln. And the reason for that is that the derivative of ln x is 1 over x. So if you use the chain rule, the derivative of ln anything, you have the anything part and then you multiply by the derivative on the top. So the derivative of ln of a function of x, so ln of f of x, like I said, using the chain rule, you've got the derivative of the outside, which is 1 over f of x, multiplied by the derivative of the inside, which is f dash x. So if you have a fraction where the derivative of the bottom is on the top, when you integrate it, you get ln of whatever's on the bottom. And that's what we're going to be doing here. We're going to make it so the derivative of the bottom is on the top. So I'm going to jump back to the top of the board. Right. First thing we've got to do is work out what this is at a half and 0 and take one away from the other. The 0 bit is easy. 4 times 0 is 0. You don't have to worry about the rest. It all comes out of 0. That should say tang, not tan. Tang. What is the inverse tang of a half? Well, what I did, I whacked it into my calculator and it didn't give me like a square root or a nice number. It gave me like a weird decimal number. And I was thinking, well, that can't be right because the answer wants it in terms of logarithms. And I thought, oh, hang on, logarithms. Is this one of the trigonometric functions that can be written as a logarithm? Some of them can. I went into my formula booklet and my formula booklet told me that the inverse tang of x is equal to a half ln 1 plus x over 1 minus x. So that's what we're going to use here to get the whole thing to work out to be an integer. Not an integer. The whole thing to work out is ln of 3 to the power of an integer over 2 to the power of an integer, or whatever it was. Right. So, a half then. 4 multiplied by a half is 2. 2 multiplied by the half here will just cancel, so we're just left with the ln. 1 plus a half is 3 over 2. And that's divided by 1 minus a half, which is a half. Cool, that's that bit done. And so this integral here, I said I want the derivative of the bottom to be on the top. So let's write that out. What would that be? And then we're going to adjust it to get back to what we had. So that would be the integral between a half and 0. Well, the bottom is 1 minus x squared. And the derivative of that would be minus 2x. So that's what we want, because that'll let us write out ln 1 minus x squared nice and easy. We don't quite have that at the moment. Instead of minus 2x, we've got 4x. Well, we can make one into the other quite easily. What do you have to do to minus 2x to get 4x? You just have to multiply it by minus 2. So minus 2 multiplied by that. And what I'm going to do is bring minus 2 outside of my integral. So minus 2 multiplied by the minus outside my integral gives me plus 2. Cool. Okay, looking nicer and nicer every second. All right. How many halves go into 3 halves? That's easy, that's just 3. So we've got ln of 3, which is good already because we know that 3's are going to be involved in the answer. Plus 2 lots of, so we said that this was ln remember modulus signs, this will have to be positive, although it doesn't actually matter here, between a half and 0. Now again, at 0, 1 minus 0 is 1, and ln of 1, so you have to think, okay, e to the power of what is equal to 1, that's 0. Actually, log of 1 is always 0. Log to any base of 1 is always 0, because anything to the power of 0 is equal to 1. That's just the logic working in reverse there. So we've got ln 3 plus 2 lots of ln, a half squared is a quarter, so that would be 3/4. And now we just have to do a bit of rules of logs to get that to the answer. So I can bring the 2 up as a power, so that's ln 3 plus ln 3 squared is 9, 4 squared is 16. And when you add logs, you multiply the inside. So that's ln of 27 over 16, which we can now write in the way that they want it. That's ln 27 is 3 cubed, 16 is 2 to the power 4. Nice one, that's the question done. That's 5 marks right there. 2 important parts to that question. The first part was selecting, when you're integrating by parts, which one is going to be u and which one is going to be dv. The question kind of gave it away, but usually that is something you have to think about. Like I said, if you've got e to the x in there, you're going to differentiate that because e to the x doesn't change. Like I said, usually though you have a look and you think, oh, I can't integrate that, so that must be the one I'm going to differentiate. It doesn't always work like that, but anyway, that's one important thing you have to think about. The other interesting bit in the question was realising that we've got x squared here, but only a single power of x here. So we can get this into the form where the derivative of the bottom is on the top. Spotting that is crucial, really, really important. So what I'd like you to do is just write up some of those integrals that come up over and over again. I'm going to show you one in the next question, but stuff like this where you have to spot a pattern or spot a trick, really important that you spot that in an exam situation. And if you'd like my help on that, just ask and I can think of, there'll be 4 or 5 patterns that you have to look out for. If you can't spot all of them yourself, just ask me, no problem. I'll give you a hand with that if you like. Okay, next question, 6b. You're actually going to see another little integration trick here that you have to watch out for, or a pattern that you should watch out for. Okay, let's get this rubbed off the board. Lovely, okay. So, it's another show that question. The answer is 61, so it doesn't really help us that much, except it will tell us right at the very end that we've got it right. What we need to do is integrate between 3 and 0, 3t multiplied by the square root of t squared plus 16 dt. Cool. Now my first thought, I didn't spot the pattern straight away. My first thought, this t squared plus 16 kind of distracted me because I was thinking, that's a square number, that's a square number. Can I do anything with the square root? Can I factorize that in any way or something like that? Can't do that. So, yeah, I forgot about that. But then I saw one of these patterns that I mentioned a couple of minutes ago, where you've got a t squared inside a bracket. Because remember, we can write this as, and it might be easier for you to spot the pattern if we do this, it's 3t multiplied by t squared plus 16 to the half. So you've got a power of t in a bracket, and then outside the bracket, you've got one less than the power of t. So it's looking like one of these integrals where what's inside the bracket, you've got the derivative of outside the bracket. And that's a pattern that you need to spot. And how we solve these is reverse integration. We sort of differentiate the bracket, see how close we are to what we want to integrate, and then see if we need to adjust it in any way. So what I did then, and I'm going to recreate what I did because you'll see what I did in a second. So how I started then is I'm going to differentiate this bracket and see what I get. And it's probably going to look close to what's inside my integral. So I started by saying, let's differentiate t squared plus 16 to the half. We'll see how close we get. We might have to adjust it. We might not. You might get lucky straight away. Probably not though. Okay. How do you differentiate using the chain rule? So I spoke a little bit about this when I was talking about ln, where you do the derivative of the outside function multiplied by the derivative of the inside function. So what's the derivative of the outside function? Well, you bring the half down in front of the bracket, and then you reduce the power by a half, and then I stopped there. And I said, oh, damn it! Damn it! That's a power minus a half. This is a power plus a half. So I've already gone wrong. I already need to go back and adjust, but you know what, that's alright, okay? So, how can I actually get this to be power plus a half? I need to increase this by 1. So let's start again, and let's change that power to 3 over 2. And I reckon that's going to look a lot better. So that power is 3 over 2, and let's try that again. We differentiate the outside function, so we bring the 3 over 2 down, times t squared plus 16, and reduce the power by 1. That's already looking a lot better. And now, because we're doing a chain rule, we have to multiply by the derivative of the inside function. The inside function is t squared plus 16, so we multiply by the derivative, which is 2t. Hang on. The 2 and the 2 here cancel out, so this gives us 3t multiplied by t squared plus 16 to the half, which is exactly what we wanted. So we don't have to adjust anymore. Usually you get to this stage and you have like a 3 here and a 6 here and you have to multiply by 2 or something. No, not this time. We don't have to adjust anymore. We've got exactly what we want. So what does that mean? If this differentiates to this, that means that this integrates to this. That's why this technique is called reverse, whatever it's called, reverse integration or reverse differentiation. I don't quite know. Okay. So the integral of that then is t squared plus 16 to the power 3 over 2. And I'm just thinking how you should lay this out. So I've written equals here, and I was a little bit naughty because this doesn't equal this. It's this integral that equals this. So the bit here where you're trying to figure out what this integrates to, that's like, as I say, that's work you do to the side of your page. It doesn't really have to be to the side of your page, but it's not like part of your main workings. It's like how you figure things out for yourself. So that's separate, and then once you've done that, you would write this out again, and you'd say the integral between 3 and 0 of 3t times t squared plus 16 to the half is equal to this. So you write down the question, do your workings out, do your figurings out to figure out what this is going to integrate to, draw a little line under it maybe, and then write the integral out again and say that is equal to this. And that's all you need to do to get all the marks there. You don't have to spend, you don't have to write anything down like, because this differentiates to this, it must mean that this integrates back to that. You don't have to write that down. They know that you know that. Cool. So, and then it's just really simple now, just putting the numbers 3 and 0 into that. I can do that quickly. T squared, 3 squared is 9, plus 16 is 25 to the 3 over 2, minus 0, whatever, 16 to the 3 over 2. How do you do powers when they're fractions? Just ask your friends in year 9. The bottom, the denominator is the root and the top bit is a power. So the square root of 25 is 5. 5 to the power 3 is 75. Minus root of 16. Have I gone wrong here? Yes, I have. Root of 25 is 5. 5 to the power 3. 5 times 5 is 25. Times 5 is 125. So 125. The root of 16 is 4. 4 to the power 3 is 64. 125 minus 64 is 61. Exactly what we wanted. 4 marks there. Great. Okay, keep your questions coming. I'll probably be popping out another video tomorrow, if you're lucky. And then maybe the next one on Monday or Tuesday next week. All right. If you have any questions, keep them coming. Like I said, I've given you a little bit of work off the back of this video to keep an eye on all the sort of integration patterns that come up over and over again. Like this one here, where you've got a power inside a bracket and then a smaller power outside the bracket, or the one we were talking about earlier, where you've got the derivative of the bottom on the top. There's a couple more that you need to be able to spot as well. So a nice little booklet or something would be good. But I can help you with that if you would like some help. Just ask. Okay. Yeah, questions, comments in the box below, in the YouTube comment box. I prefer it that way because then other people can see it and they know that other people watch this video. You know, if you just email me, only I see that. Yeah, okay. Right, I think that's it from me. Good luck. We're getting closer to crunch time now, aren't we? It's April, and the exam is at the end of, I think it's at the end of June, AQA FP2. So yeah, really time to start cranking the old past papers out. Good luck.